I want you to do something for me right now. Just look at the device you are using to listen to this.
Hmm.
Maybe it's a smartphone in your hand or, maybe a laptop sitting on your desk. And it feels incredibly fast, doesn't it?
Oh, yeah.
I mean, it can stream 4K video without buffering. It handles your email, runs complex games with realistic lighting. It basically feels like magic. But here is the hard truth that is currently keeping chip architects and physicists up at night.
The wall.
Exactly. That device is hitting a wall, a physical hard wall. We are literally reaching the end of the line for the way we've built computers for the last, 70 years?
Yeah, about 70 years. And I know it sounds dramatic, like something out of a disaster movie or something, but it is entirely accurate. We have spent decades shrinking transistors, packing them tighter and tighter.
Like trying to fit more people into a subway car?
Right. Perfect analogy. But we are actually running out of space. We are down to the atomic level now. And when you get that small, the rules of reality itself, they just change.
And that is exactly where we are going today. We are stepping beyond classical bits. We are going to talk about a technology that doesn't just make computers faster, it makes them fundamentally different. So today, we are doing a deep dive into quantum computing fundamentals.
Which is honestly a favorite topic of mine, because it forces us to rethink what information actually is. It is not just distinct little packets of data anymore.
No, it's really not. And we are going to be guided today by a really comprehensive analysis provided by Swati Karni and Arun Kumar Rajamandrapu. Their work is essentially the backbone of our discussion today.
And they did a fantastic job. They laid this out in a way that, thankfully, doesn't require a PhD in theoretical physics to follow.
Right, which I appreciate, although I will warn you, listener, we are going to stretch our brains a bit today. But the mission here is to move past the buzzwords. Because, everyone has heard qubit and entanglement.
Usually in sci-fi movies.
Exactly. Right before the spaceship explodes or they travel through time or whatever. But we want to understand the actual mechanics. Why does a quantum computer have to be colder than outer space to work? Why does it change everything from medicine to cybersecurity?
And why it is no longer just a theory. As Carney and Rajamandrapu point out, we are transitioning from blackboard math to engineering reality. We are actually building these things now.
Okay, so let's unpack this. I mentioned a wall earlier, the classical limit. Why is my smartphone hitting a dead end? Because from where I sit, it seems like every single year, Apple or Samsung releases a faster phone. Are you saying that is just going to stop?
It is going to slow down dramatically.
Yeah.
And eventually, yes, it will hit a hard limit. It really comes down to something called the atomic wall. But to understand that, we have to look at the history of computing, which has largely been defined by Moore's law.
Okay, Moore's law. I know this one. It's the idea that computing power, or specifically the number of transistors on a chip, doubles every 2 years or so.
Roughly, yeah.
Right, and it's why the phone in my pocket is massively more powerful than the computer NASA used to send Apollo to the moon.
Exactly. Gordon Moore observed this trend way back in the 60s. But here's the thing that people forget. Moore's law isn't a law of physics. It's an observation of economics and manufacturing.
Ah, okay.
And that observation is decelerating. We are facing physical limits. The first major one being heat.
Heat, like the phone getting hot in my hand.
Yes, but on a microscopic scale. Think about it. A computer chip works by pushing electrons through tiny wires. Resistance generates heat. When you pack billions of transistors into a space the size of your fingernail, the heat density becomes completely unmanageable.
Wow.
If we kept following Moore's law strictly, without fundamentally changing the technology, our chips would eventually get as hot as the surface of the sun. You can't just keep packing things tighter without melting the silicon.
Okay, so we are essentially cooking the processors, but that seems like an engineering problem, right? Just get better fans or use liquid cooling or something.
We can do that to an extent, and we do. But the second barrier is the atomic barrier, and this one is fundamental physics. We are manufacturing transistors right now that are just a few nanometers wide. A silicon atom is about 0.2 nanometers.
Wait.
So we're talking about features on a chip that are maybe 10 or 20 atoms wide.
That is just unfathomably small.
It really is. And at that scale, classical physics, the physics of Isaac Newton, predictable balls rolling down hills, it simply fails.
Fails how? Like gravity stops working.
Well, electrons stop behaving like tiny ping pong balls that stay in their lanes. They start behaving like waves. They start doing things like quantum tunneling.
Tunneling. That sounds like a cheat code in a video game.
It basically is a cheat code, but it's a cheat code that breaks our computers.
Yeah.
Look, in a classical transistor, you have a gate that stops the flow of electrons. It's your off switch.
Right.
But if the gate is too thin, like literally just a few atoms thick, The electron, because it is behaving like a wave, can just tunnel right through it. It effectively teleports to the other side.
So your off switch is leaking electricity.
Exactly. If you can't reliably turn a switch off because the electrons just ghost right through the wall, you can't represent a zero. Your basic logic falls apart. You can't build a reliable computer when the electrons refuse to follow the old rules.
That sounds like an absolute nightmare for companies like Intel or AMD. It's not that their engineers aren't smart enough, it's that nature itself is saying stop.
Precisely. Nature is putting up a roadblock. And on top of that, you have the von Neumann bottleneck.
Ah, the bottleneck. This is architectural, right?
Correct. Most classical computers, basically everything you and I use today, are built on the von Neumann architecture. You have a processor, the CPU over here, and memory, the RAM, over there. They are physically separate real estate on the motherboard.
Okay, got it.
So to do any calculation, the CPU has to ask the memory for data. The memory sends it over a bus, which is just a data path. The CPU does the math and then sends the answer back to memory.
So there's a constant commute happening.
A massive, constant commute. And they share that path. It physically restricts transfer rates.
Right.
It's like having a Ferrari engine, but you are stuck in a single-lane tunnel.
Yeah.
You spend way more time moving data back and forth than you do actually processing it. This caps performance, specifically for exponential problems. It's a traffic jam built into the architecture itself.
So let's recap this classical limit. We have chips that are getting too hot to handle, transistors that are leaking electrons because they're too small, and an architecture that creates built-in traffic jams. It really sounds like we need a clean slate.
And that clean slate is what quantum computing is. It's not an upgrade. It's a total paradigm shift. We are finally accepting that at the atomic level, the universe just works differently. And instead of fighting those weird rules, we are going to build a computer that uses them.
Let's look at that contrast, because I think a lot of people assume a quantum computer is just a supercomputer, like it's just a faster version of my laptop. If my laptop is a bicycle, a supercomputer is a race car. Is a quantum computer just a rocket ship?
No, that is completely the wrong analogy. If a classical computer is a race car, a quantum computer isn't a faster vehicle at all. It's a teleportation machine. It operates on entirely different physics.
Okay, I like that. Let's break down those differences. Classical versus quantum.
Sure. A classical computer, like your laptop, relies on linear processing. It does things one after another. Step one, then step two, then step three. It is deterministic.
Deterministic, that means predictable, right?
Yes. Meaning if you give it input A, you will always get output B. It is totally reliable, and it's built on bits. A bit is strictly 0 or 1, on or off, true or false.
Right. And everything digital in our world, from this audio recording to the entire internet, is just billions of zeros and ones strung together.
Precisely. Now, contrast that entirely with quantum. Quantum computing features exponential scaling. It isn't deterministic in the same way. It is probabilistic. It relies on probability amplitudes, not absolute certainties. And it is built on qubits.
There is a quote in the Carney and Rajamandrapu source material here that I love. They wrote, "Quantum can no longer be called a theory since it is soon going to be viable and powerful." That feels like a real line in the sand.
It is a line in the sand. It is saying we are done just thinking about this on chalkboards in university basements. We are actually building it. But to understand how we build it, we have to understand the qubit. This is where we leave the world of the switch and enter the world of the vector.
Okay, vector space versus the switch. This is a key distinction in their analysis. I think I get the switch, the classical bit. It's a light switch. It is up or it is down.
Yes, simple, binary. Now, I want you to visualize something entirely different. Imagine a sphere, a ball.
Okay, I'm picturing a ball, like a globe.
Exactly like a globe. In classical terms, the bit can only be at the North Pole, which we will call 0, or the South Pole, which we call 1. Nowhere else. You can't be in Brazil. You can't be in France. You're at the pole or you're at the other pole.
Got it. North or south, nothing in between.
But a qubit, or quantum bit, exists in what we call a two-dimensional Hilbert space. Visually, think of it as a vector, an arrow, that starts at the dead center of the globe and points out to the surface.
And that arrow can point anywhere.
Anywhere on the surface, it can point to the North Pole, the South Pole, or anywhere along the equator or any angle in between the two. This allows for multi-dimensional information storage. Instead of just a simple yes or no, you have a complex coordinate. It interacts with complex probability amplitudes.
So if a classical bit is a coin that is glued to the table showing heads, a qubit is what?
That brings us to the absolute perfect analogy for superposition, the spinning coin.
Oh, I love this analogy because I can actually visualize it in my head.
Right, so take that coin off the table, Flick it high into the air. While it is spinning up there, is it heads or tails?
It's neither, or both. It's just a blur.
Exactly. While it is wobbly and spinning in the air, it is in a state of superposition. It is both heads and tails simultaneously until it falls and settles on the table. In quantum mechanics, we represent this mathematically. The notation is the Greek letter psi equals alpha times the 0 state plus beta times the 1 state.
Okay, wait. Let's pause on the math. I see the Greek letters in the outline. Let's not gloss over this, because the critique of these kinds of deep dives is usually that we skip the hard stuff. What are alpha and beta actually doing there?
I'm really glad you asked that. In a classical probability, you would say there is a 50% chance of heads and a 50% chance of tails. Those are just positive numbers that add up to 100%. But in quantum mechanics, alpha and beta are what we call probability amplitudes. And here's the kicker.
Oh.
They can be complex numbers. They can actually be negative.
Negative probability. What does it even mean? Like, I have a negative 50% chance of winning the lottery.
It completely doesn't make sense in our macroscopic everyday world. But in the math, it allows for something called interference. Think of noise-canceling headphones. How do they work?
They create a sound wave that is the exact opposite of the outside noise, right? And the two waves cancel each other out to make silence.
Exactly. That is destructive interference. Because quantum states are described by these waves, these amplitudes. A negative amplitude can literally cancel out a positive amplitude. This is the secret sauce of quantum computing. A quantum computer doesn't just try every possible answer at once like people think. It orchestrates these waves so that the wrong answers interfere destructively, they cancel out, and the right answer interferes constructively. It amplifies.
That is actually mind-blowing. So it is not just getting lucky. It is using the math of waves to actively kill the wrong answers.
Yes, the coin is spinning, and we are manipulating the air currents around it so that when it finally lands, it is statistically guaranteed to land on the side we want.
Okay, so that is superposition. It's the spinning coin, but utilizing wave math. Now, let's talk about the other truly spooky concept, entanglement.
Spooky action at a distance. Those were Albert Einstein's exact words. He hated it.
Why did Einstein hate it?
Because it implies that information can travel instantly across space, which seems to violate the cosmic speed limit, the speed of light. Entanglement is a mechanism where two individual qubits become intrinsically linked.
Linked how? Like with a microscopic wire?
No wire. They are fundamentally linked in their quantum state. They share a single mathematical existence. If you entangle two qubits, they stop being two separate objects and become one unified object. If you measure one, you instantly know the state of the other, regardless of the physical distance between them.
Give me a real-world example, or, a semi-real-world one to help me picture it.
Imagine you have a pair of gloves. You put the left glove in a box and the right glove in another box. You mail one box to New York and you mail the other box to an astronaut on the moon.
Okay, tracking.
If the person in New York opens their box and sees a left glove, they instantly know the box on the moon contains a right glove. That is classical correlation. The gloves were already determined before you even mailed them.
Right. There's no magic there. The left glove was always the left glove.
But quantum entanglement is entirely different. In the quantum version, the gloves don't actually have a shape while they are inside the boxes. They are both in a superposition of being left and right simultaneously. But the exact moment the New York person opens the box, the glove forces itself to become, say, left. Instantly, at that exact same nanosecond, the glove on the moon forces itself to be right.
See, that is the spooky part. The decision of what shape to be is made at the moment of measurement, instantaneously across a massive distance.
Exactly. And the source material notes this perfectly. They say, a happening to one will immediately change the other as well.
So what does that actually do for a computer? Because if I can't use it to send a text message faster than light, because I assume we still can't do that.
Correct. You can't send usable data faster than light. That breaks relativity. And we can't do that. But you can use it for incredibly synchronized processing. In a classical supercomputer, all the individual processors have to constantly talk to each other to coordinate, hey, I finished my part of the math, are you done? That communication takes time. We call that latency. With entangled qubits, they act as a single, unified system. They dance in perfect unison without needing to send electrical signals back and forth.
So it is essentially a hive mind.
A perfect hive mind. If you change one part of the system, the whole system reacts instantly. This allows for a level of massive parallelism that classical computers just can't touch.
Okay, so we have superposition, the spinning coin with waves, and entanglement, the hive mind. Now, we need to map this out. We talked about the sphere earlier, the globe analogy. This is formally called the block sphere.
Right. The block sphere is the standard geometric representation of a single qubit state. It's how scientists and engineers visualize what they are actually doing to the data.
So let's go back to our globe. Walk us through the geography of it.
Sure. The North Pole is the 0 state. The South Pole is the 1 state. Now remember our vector, that arrow starting from the center of the Earth. The arrow points to a specific spot on the surface. That spot is mathematically defined by two angles, theta and phi.
That sounds exactly like latitude and longitude.
It basically is latitude and longitude. Theta corresponds to latitude, how far north or south you are from the poles. This determines the overall probability of measuring a 0 or a 1. If you are sitting exactly on the equator, you are at 90 degrees, and you have a perfect 50-50 chance.
And phi, the longitude.
Phi is the phase. This is your direction around the equator. Now, this doesn't change the probability of being 0 or 1, but it is absolutely crucial for that interference we talked about earlier. It is what allows qubits to interact with each other in those complex wave-like ways. It is the wave part of the equation.
So when we are programming a quantum computer, we aren't just typing lines of code. We are mathematically moving this arrow around the surface of the sphere.
Exactly. And we do that using quantum gates.
Which brings us to the next section of the outline, rotating the sphere. This is how we actually perform computation.
Right. In classical logic, we use Boolean gates. AND or not T, and they're irreversible. Think about a classical OR gate. If I tell you the output of the gate is true, do you have any way of knowing if the input was true and false, false and true, or true and true?
No, that information is just gone.
Exactly. Information was lost, so you can't reverse the process. But quantum gates are fundamentally reversible. They are unitary matrices. Visually, a quantum gate just takes that vector on the block sphere and rotates it. It never destroys the underlying information. It just moves it to a completely new coordinate on the sphere.
So a gate is literally just a specific rotation command, like telling the arrow, rotate 90 degrees to the right.
Yes. Let's look at the most famous one mentioned in the Carney and Rajamandrapu source. The Hadamard gate, just capital H.
The H gate. It sounds like a superhero gadget.
It really is the most important gadget we have in quantum logic. The Hadamard gate's entire function is to put a qubit into superposition. If you start with a qubit sitting at the North Pole, the 0 state, completely still, and you hit it with a Hadamard gate, it rotates the vector precisely down to the equator.
Down to that 50-50 line.
Correct. It takes a definite predictable state and makes it wobbly. It creates that exact 50-50 probability. It is the electronic equivalent of flicking the coin up into the air. Without the Hadamard gate, you simply don't have quantum computing. You just have a really complicated, really expensive classical computer.
So you use these various gates to spin the coins up, entangle them together, rotate them around to do your interference calculation, and then you measure it.
And then you measure it, which forces the coins to land. But doing this physically is incredibly, incredibly difficult. Which brings us to the actual hardware.
The hardware is fascinating. I'm looking at a picture in the research of a dilution refrigerator. It literally looks like a giant, intricate golden chandelier.
It is an absolute masterpiece of engineering. And it has to be, because of the extreme temperature required. 15 millikelvin.
15 millikelvin. Can you put that in perspective for us? Because I know it's cold, but how cold?
Okay. Outer space, the deep, empty void between stars, is about 2.7 Kelvin. That is unimaginably cold. But 15 millikelvin is a fraction of a degree above absolute zero. It is literally thousands of times colder than deep space. Absolute zero is the theoretical point where all atomic motion completely stops.
Why? Why on earth do we need to turn the thermostat down that low? Are the quantum chips just running that incredibly hot?
No, it is not about cooling the chip because it is generating heat. It is about silence. We are using superconducting qubits. We have to completely isolate them from any thermal noise.
Thermal noise, meaning what exactly?
Heat is just vibration. It is atoms jiggling around. If an atom jiggles near our qubit, it creates noise. It bumps into the qubit. And remember, our qubit is a very delicate spinning coin. If a hot air molecule bumps into it,
The coin falls over prematurely.
the coin falls over. The superposition collapses before we are done with the math. The magic stops working. So we use these massive golden refrigerators, which use a complex mix of helium-3 and helium-4 isotopes to create an absolute vacuum of cold and silence. So the qubit can think without being disturbed.
And even with all that extreme cold, we still have a major problem. The outline calls it the enemy.
Decoherence.
Decoherence. I gotta say, it sounds like a really bad breakup.
It sort of is. It is the breakup of the quantum state. Qubits are extremely fragile. Triggers like the slightest bit of heat, microscopic vibration, or even stray electromagnetic waves like a Wi-Fi signal passing through the room can cause the quantum state to collapse.
So if someone literally sneezes in the next room,
Well, the physical shielding is better than that, but effectively, yes. A random cosmic ray hitting the chip from space can completely ruin the calculation. And this fragility leads us to the constraint we are living in right now in the industry, the NISQ era.
that's NISQ, noisy intermediate scale quantum.
Right. Ideally, we want fault-tolerant quantum computing. We want perfect qubits that never, ever make mistakes. We aren't there yet. We're in the noisy era. The computers work, but they make errors. The qubits decohere very quickly. You have very short time, window microseconds, to do your math before the coin just falls over on its own.
So how do the engineers deal with that right now?
Massive error correction. The main solution right now is to group a bunch of physical noisy qubits together to form one single logical qubit. You use the group to constantly police each other.
Oh, I see. It's like having 10 people shouting the answer to a math problem, and you just assume the real answer is whatever the majority is shouting, because one or two might have messed up.
That is a remarkably good way to look at it.
Yeah.
But it means you need thousands of physical qubits just to get a few reliable logical ones. It is the biggest engineering hurdle in the field today.
Okay, here is where it gets really interesting for the applications. Let's do a showdown. Comparison time. Classical versus quantum capabilities. We have a great table here in the Carney and Rajamandrapu analysis. Let's run through it feature by feature.
Let's do it.
Feature 1, processing. Classical is sequential. Quantum is simultaneous. I think we covered that with the library analogy earlier.
Right, reading one book at a time versus comprehending the entire library all at once.
Feature 2, search method. Classical uses exhaustive search.
Checking every single box one by one. If you lost your keys in a massive 1,000-room hotel, classical search means opening door 1, checking, then door 2, checking, then door 3.
And quantum uses quadratic speedup, specifically using Grover's algorithm.
We'll dig into the mechanics of Grover in a minute, but essentially, the quantum search can statistically check multiple rooms at the same time and highlight the keys.
Okay, feature 3, data unit. Binary bits versus multidimensional vectors. We've definitely covered that with the sphere. Feature 4, optimization. Classical uses heuristics.
Heuristics are basically best guesses. When a problem is too mathematically hard for a classical computer like figuring out the absolute most efficient route for a delivery truck that has 1,000 stops, it cheats. It uses an algorithm to find a good enough answer. It doesn't find the perfect one because checking every single route combination would take 1 billion years.
And quantum.
Quantum finds the ground state, the absolute mathematically perfect best answer. Because instead of guessing, it can flow through the entire landscape of possibilities like water flowing down a mountain and naturally settle in the absolute deepest valley, which is the optimal point. It doesn't guess, it flows.
That is a colossal difference for industries like logistics or finance. But let's talk about the specific mathematical algorithms that make this happen. Algorithms of change. The first one is basically the celebrity of the quantum world, Shor's algorithm.
Peter Shor completely changed the world with this one back in 1994. The function is easily stated. It factors large integers exponentially faster than any classical method.
Factoring integers. I mean, that sounds like fourth grade math. What are the factors of 15, 3, and 5? Why is a fourth grade math problem a literal threat to national security?
Because the lock on the entire Internet's front door RSA encryption relies entirely on the difficulty of factoring incredibly large numbers.
Unpack that for us so we understand the stakes.
When you send your credit card number to Amazon or send a secure text message, it is encrypted using a massive number. Let's say it has 400 digits. That public number is the product of two huge prime numbers multiplied together. To hack the code and read your credit card, you have to figure out what those two original prime numbers were.
And a normal computer's just bad at this.
Terrible. To find the factors, a classical computer basically has to divide that massive number by every possible prime number until it finds a match. For a 400-digit number, that brute force method would take thousands of years. It is safe purely because the math is hard and tedious.
But Shor's algorithm completely changes the math.
Yes, and this is where we need to be very specific about what Shor did. He didn't just write a faster division program. He transformed the nature of the problem. He realized that factoring numbers is mathematically related to finding the period of a repeating function.
The period, like a repeating pattern in a sequence.
Exactly. Think of a sine wave repeating over and over. Shor realized you can turn the factoring problem into a period-finding problem using modular arithmetic. And quantum computers, because of their wave nature, are insanely good at finding periods through that interference we talked about.
The noise-canceling headphones effect.
Yes. When you run Shor's algorithm, you put all the possible answers into a massive superposition. Then you perform this modular exponentiation operation. The wrong periods, the random mathematical noise, interfere destructively with each other and completely cancel out. The correct period, the true pattern hidden in the numbers, interferes constructively and amplifies itself.
So the right answer literally just rises out of the noise.
It does. And once you have the period, a classical computer can easily, in seconds, calculate the prime factors. Shor's algorithm reduces the cracking time from thousands of years down to hours. The mathematical notation is big O of log n cubed. That is the proof of the exponential speedup.
So essentially, RSA encryption is dead.
Once we have a quantum computer stable enough and with enough logical qubits to run Shor's algorithm, yes, RSA is completely dead. That is exactly why there is a massive global rush for post-quantum cryptography, or PQC, right now. We're actively trying to invent entirely new math problems that even a quantum computer can't solve easily, usually involving multidimensional geometry like lattices.
Okay, so Shor's breaks the codes. What about the search function? We mentioned Grover's algorithm earlier with the hotel keys.
Right, Grover's algorithm is specifically for searching unstructured databases.
Unstructured meaning, like a total mess.
Meaning a list that has no order, isn't alphabetized, nothing. Imagine a massive phone book where the names are printed in completely random order. If you want to find the name Smith, you can't jump to the S section. You have to read every single line until you find it.
That sounds like a nightmare.
It is. But Grover's provide the quadratic speedup, mathematically noted as big O of the square root of n.
Let's use the concrete example from the slide. Give us the numbers.
Okay, if you were trying to find one specific item hidden in 1 million unstructured items, a classical computer has to check, on average, half of them, 500,000 times before it stumbles on the right one. Grover's algorithm can find that exact item in about 1,000 steps.
500,000 steps versus 1,000 steps. That is a massive difference in computing time. How does it actually do it? Is it that interference trick again?
It is. It uses a very specific process called amplitude amplification. Imagine you have 1 million normal needles and 1 magnetic needle in a haystack. Grover's algorithm doesn't pick up the hay piece by piece. It makes the magnetic needle vibrate.
Okay, I like that visual.
It applies an oracle function that mathematically flips the phase of the correct answer, the needle. Then it uses a diffusion operator, which acts almost like a mirror. It reflects all the amplitudes around the average. Because the correct answer was flipped backward, this reflection process massively boosts its amplitude, its probability, and shrinks the amplitude of all the hay.
So every time you run that cycle, the needle gets louder and the hay gets quieter.
Exactly. You run it about 1,000 times for 1 million items, and the probability of measuring the needle is nearly 100%.
So what does this all mean for us? We have world-ending code breaking, we have super search capabilities, but there is a lot more. Section 13 of the analysis, applications beyond computation.
This is where it gets genuinely exciting for humanity. Beyond just breaking spies codes or searching databases, we can actually save lives. Let's talk about medicine.
They mentioned simulating molecular interactions.
Right. Right now, designing new pharmaceutical drugs is largely trial and error. We can't accurately simulate a complex molecule on a classical computer because the molecule itself is a quantum system. Even a basic caffeine molecule is wildly complex. The electrons interact in quantum probabilistic ways. A classical computer has to guess and approximate that behavior. It's like trying to simulate a Category 5 hurricane using a wooden slide rule.
It's just way too complex for binary bits.
But a quantum computer is a quantum system. It follows the exact same rules as the molecule does, so we can model nature exactly as it is. We could design drugs that target a specific virus protein with absolutely perfect accuracy without doing years of blind lab testing. We could fold proteins virtually.
That truly changes everything in healthcare. What about material science?
Same exact principle. Designing lightweight alloys for airplanes or inventing new batteries. We all want better batteries for electric cars and grid storage, right? We need to understand the chemical interactions at the quantum level to truly optimize energy density, or take something basic like fertilizer.
Fertilizer. How does quantum computing help grow corn?
The Haber process is how we create ammonia for fertilizer today. It consumes massive, huge amounts of the world's energy output because it requires extreme heat and extreme pressure. But tiny bacteria in the soil do the exact same thing at room temperature using an enzyme called nitrogenase.
And we just don't know how the bacteria do it.
We know what they do, but the actual mechanism involves incredibly complex quantum electron transfers that our supercomputers cannot simulate. If a quantum computer can map and crack that quantum mechanism, we could figure out how to produce fertilizer with almost zero energy cost. That solves a global food crisis and an energy crisis at the same time.
That is incredible. What about finance?
Portfolio optimization, going back to that ground state we talked about. Finding the absolute perfect, mathematically best balance of risk and reward in a wildly complex, shifting global market. Also, fraud detection, spotting tiny hidden patterns in a chaotic sea of transactions using that Grover-like pattern matching ability.
So, where are we on the timeline for all of this? The final section here is the quantum supremacy era.
Quantum supremacy is a bit of a controversial term in the industry, but it broadly refers to the milestone where a quantum computer finally does something, anything, that a classical supercomputer simply cannot do in a reasonable amount of time.
Google made a massive claim about this a few years ago.
They did with their Sycamore processor. They officially reported cracking a specific random number generation problem in 200 seconds.
200 seconds, just over 3 minutes.
Right, and they estimated that the exact same problem would require the world's fastest classical supercomputer 10,000 years to solve.
That is the literal definition of supremacy, 200 seconds versus 10 millennia.
Now, IBM pushed back on that paper and said, actually, if we heavily optimize the classical supercomputer, we can probably do it in 2.5 days. But even if you accept IBM's math, 200 seconds versus 2.5 days is still a staggering, massive gap. And that gap is only widening. We're seeing hardware growth that is accelerating rapidly. Back in 2007, a company called D-Wave was looking at 28 qubits. Just recently, we've seen IBM's Osprey processor drop with 433 qubits.
That growth curve is going completely vertical.
It is. And as the Carney and Rajamandrapu analysis concludes so beautifully, we are not just building faster computers, we are unlocking a new understanding of the universe.
That really feels like the perfect place to start wrapping this up. We have gone on quite a journey today. From the impending heat death of Moore's law and melting processors to the freezing cold of the 15 millikelvin chandelier fridge, we've spun coins, entangled particles across space, and mathematically rotated vectors on the Bloch sphere.
It is a profound journey from the bit to the qubit, from the simple switch to the multidimensional vector.
And the so what here? Why you, the listener, should care about any of this is just huge. This isn't just about rendering faster video games or getting your email quicker. It is about solving monumental problems, like precise molecular simulation and zero-energy fertilizer that are currently mathematically impossible. It is about unlocking parts of science that have been locked behind a door purely because we simply didn't have the right key.
The key is the qubit, and we are finally, just now, learning how to turn it.
Here is a final provocative thought for you to chew on, listener, as we sign off. We talked extensively today about how quantum computers physically manipulate probability and vectors to find answers. They literally manipulate the fundamental fabric of reality to process information. If the universe fundamentally operates on these exact same quantum rules, superposition, entanglement, interference, then is the universe itself just a massive cosmic information processor? When we build these supercooled quantum machines, are we just building a microscopic version of the reality we already live in?
Oh, man. That is a dangerous, deep question to ask before lunch. But honestly, it is the right question. If nature computes, then building a quantum computer is the ultimate act of biomimicry. We aren't fighting physics anymore. We are finally learning to speak nature's true language.
Thank you so much for taking this deep dive with us. We will see you in the next one.
Stay curious.